We have seen the edge of everything. 93 billion light-years from end to end, a sphere of galaxies and light and ancient starfire stretching in every direction around us. 2 trillion galaxies mapped, light from 13.8 billion years ago, captured and analyzed. The observable universe laid out like a cosmic inventory, catalogued, measured, understood. And then the measurements stop. Not because we ran out of telescopes or patience or funding, but because physics itself draws a line and says no further. Beyond that horizon, there is only silence. But here is the question no one can answer with certainty. What is that silence hiding? Some scientists will tell you it is more of the same. Infinite space, infinite galaxies, stretching on forever in every direction, forever beyond our reach. Others will tell you it is nothing. Not empty space, but the absence of space itself, a boundary where reality simply ends and the rules that govern existence dissolve into something we do not have words for. And then there are those who will tell you it is neither. That beyond our bubble of visibility, there are other bubbles, other universes with other laws, other dimensions we cannot perceive, other versions of physics playing out in realms we will never touch. The James Webb Space Telescope has let us see closer to the beginning than ever before, 13.4 billion years into the past. Galaxies that formed when the universe was practically an infant. And yet the deeper we look, the stranger the picture becomes. Because the data is not showing us a simple, well-behaved cosmos. It is showing us tensions, contradictions, hints that something fundamental about our model is incomplete. So what lies beyond the edge, and what does it mean that we may never, ever know? Welcome to Magnetic Space. If you're new here, please subscribe. We make these documentaries every day, and honestly, we'd love to have you along for the ride. Before we begin, tell us in the comments where you're watching from and what time it is there. Now settle in. This is going to be a good one. The observable universe is 93 billion light-years wide. That number should feel wrong to you. It should feel impossible. The universe is 13.8 billion years old. Light has been traveling toward us for 13.8 billion years. So the farthest thing we should be able to see is 13.8 billion light-years away. The math is simple. The answer should be obvious, and yet the actual number is 46. 5 billion light-years in every direction. Double that, and you get 93 billion light-years across. Somewhere between the simple math and the real answer, something happened that most people never stop to think about. The universe cheated. Not in a way that breaks the rules, but in a way that bends them so thoroughly that the result looks like a mistake. It isn't. This is the story of the visible frontier, the boundary of everything we can ever see, everything we have ever seen, and everything we will ever be able to observe, no matter how long we wait or how powerful our telescopes become. It is the edge of perception itself, and it is not where you think it is. Let's start with what the observable universe actually is, because the name is more literal than it sounds. The observable universe is not the universe. It is the portion of the universe from which light has had enough time to reach Earth since the beginning. Picture yourself standing in the middle of an enormous dark field at night. You turn on a flashlight. The beam travels outward at the speed of light, illuminating everything it touches. But the field is so large that the light hasn't reached the far edges yet. The part of the field you can see, the part lit by your beam, that's your observable region. Everything beyond that is still there. It's just dark to you. The universe works the same way, except the flashlight is the Big Bang, and the beam has been traveling for 13.8 billion years. Now, here's where it gets strange. The observable universe is a sphere, not a disk, not a plane, a sphere. And you are sitting exactly at the center of it. So is everyone else. Your neighbor is at the center of their own observable universe. An alien on a planet orbiting a star in the Andromeda galaxy is at the center of theirs. A hypothetical observer floating in the void between galaxy clusters, completely alone in the dark, is at the center of theirs. This is not because any of you are special. It's because the observable universe is defined by the observer. It is the region of space from which light has had time to reach you. The boundary is set by how long light has been traveling and how fast it moves. Since light travels at the same speed in all directions, the result is a sphere with you at the center. Move 1 billion light years to the left, and the sphere moves with you. You're always in the middle. Not because you're standing still, but because the definition of the edge is tied to where you are. The edge itself is called the particle horizon, though some scientists prefer the term cosmic horizon. It's not a wall, it's not a surface. You can't touch it, you can't see it, and if you somehow traveled toward it, you would never reach it. The horizon is an observational limit, not a physical one. It marks the boundary between the part of the universe we can observe and the part we cannot, and that boundary shifts depending on where and when you are. Think of it like the horizon on Earth. When you stand on a beach and look out at the ocean, you see a line where the water meets the sky. That line is not a real edge. It's just the farthest point you can see from where you're standing. Walk forward, and the horizon moves with you. The particle horizon works the same way, except instead of being limited by the curvature of the Earth, you're limited by the age of the universe and the speed of light. So why is the observable universe 93 billion light-years across, if the universe is only 13.8 billion years old? This is where most explanations fall apart, where the math starts to feel like a magic trick. The answer has nothing to do with light moving faster than it should, or time behaving strangely. It has everything to do with space itself. Space expands. It always has. From the moment of the Big Bang, the fabric of the universe has been stretching, pulling galaxies apart, increasing the distance between any two points that aren't held together by gravity. And while that expansion was happening, light was traveling. A galaxy that emitted light 13 billion years ago was much closer to us when that light began its journey. Let's say it was 5 billion light-years away at the time. The light started moving toward us at the speed of light, but while the light was in transit, space kept expanding. The galaxy that emitted the light drifted farther away. The space between us and that galaxy stretched. By the time the light finally reached Earth 13 billion years later, the galaxy that sent it was no longer 5 billion light-years away. It was 30 billion light-years away, maybe more. The light still took 13 billion years to get here because it was traveling at the speed of light the whole time. But the distance between us and the source of that light grew while it was traveling. Run that process across the entire history of the universe, and the math starts to make sense. The farthest light we can see today was emitted by regions of space that were relatively close to us when the universe was young. Over the billions of years that light spent traveling, those regions moved farther and farther away due to the expansion of space. Today, Those regions are roughly 46.5 billion light-years from Earth in every direction. The light took 13.8 billion years to arrive, but the source of the light is now vastly more distant than it was when the photons left. This is not a violation of the speed of light. Light still travels at exactly the same speed it always has. Space is just bigger now than it was when the journey started. If space had not expanded, the farthest visible regions would be exactly 13.8 billion light-years away. The diameter of the observable universe would be 27.6 billion light-years. Clean, simple, intuitive. But space did expand, and the current distance to the edge of the observable universe is 46.5 billion light-years. The diameter is 93 billion light-years. That's the actual size of the region we can observe, the actual span of the visible frontier. Light from anything farther than that has not had enough time to reach us yet, and because the universe is expanding faster every year, some of that light never will. There's a boundary inside the observable universe that deserves its own mention. It's called the surface of last scattering, and it's the oldest thing we can see. When the universe was about 380,000 years old, it was still a hot, dense fog of hydrogen plasma. Photons couldn't travel freely because they kept bouncing off charged particles. Then the universe cooled enough for protons and electrons to combine into neutral hydrogen atoms. Suddenly, photons could move without interference. The universe became transparent. The light from that moment, stretched by billions of years of expansion, is what we now detect as the cosmic microwave background. It's a faint glow of radiation coming from every direction in the sky, the afterglow of the moment the universe went from opaque to clear. The cosmic microwave background marks the edge of the observable universe in a practical sense. We cannot see anything older than 380,000 years after the Big Bang, because before that moment, the universe was a wall of glowing fog. No telescope, no matter how powerful, can see through it. It's like trying to see past the surface of the sun. The light just scatters. So the observable universe has two edges. One is the particle horizon, the theoretical limit set by the age of the universe and the speed of light. The other is the surface of last scattering, the practical limit set by the fact that the early universe was opaque. They're not the same thing, but they're close. The cosmic microwave background sits just inside the particle horizon, about 46 billion light-years away in present-day distance. It's the oldest light we can detect and the farthest back in time we can see. Beyond that boundary, the universe still exists. We just can't observe it. Not now, not ever. Let's talk about scale, because 93 billion light-years is a number so large that it doesn't mean anything to a human brain. You need comparisons. You need something to anchor it to. Start with the distance from Earth to the Sun, about 93 million miles. Light takes 8 minutes to cross that distance. Pluto, at its farthest, is about 40 times farther out. Light takes roughly 5.5 hours to get there. The nearest star beyond the Sun, Proxima Centauri, is about 24 light-years away. Light takes 24 years to make the trip. The Milky Way galaxy, our home, is about 100,000 light-years across. Light takes 100,000 years to travel from one side to the other. The Andromeda galaxy, our nearest large neighbor, is about 5 million light-years away. Light takes 5 million years to cross the gap. Now multiply that distance by 18,000 and you're roughly at the edge of the observable universe. 46. 5 billion light years. Every star, every galaxy, every cluster, every supercluster, every filament of matter threading through the cosmic web, all of it sits somewhere inside that sphere, and all of it is expanding away from us. The farthest galaxies we can currently observe are so distant that we see them as they existed more than 13 billion years ago, when the universe was less than a billion years old. They were small, dim, chaotic. By now, today, in the present moment, those galaxies are unrecognizably different. They've merged with other galaxies, formed trillions of new stars, and drifted so far away that the light showing us their current state won't reach Earth for tens of billions of years. We are not looking at the universe as it is, we are looking at the universe as it was. Every photon that hits a telescope on Earth is a fossil, a relic from a moment that ended billions of years ago. The farther out we look, the farther back in time we see. The edge of the observable universe is also the edge of observable time. There's something deeply unsettling about that. You are sitting in a bubble 93 billion light-years wide, surrounded by a horizon you can never cross, looking at light from objects that no longer exist in the form you're seeing them. And outside that bubble, the universe continues. Galaxies you will never see are forming, evolving, dying. Stars are igniting. Planets are cooling. Maybe life is starting. Maybe civilizations are rising. Maybe someone out there is pointing a telescope in your direction and seeing the Milky Way as it existed billions of years ago, a younger, smaller version of itself. You will never know. They will never know. The observable universe for them is a different sphere, centered on them, containing a different set of galaxies. Your observable universe and theirs might overlap, or they might not. If they're far enough away, there is no overlap at all. You exist in completely separate visible regions of the same universe, forever isolated by distance and time. Here's the uncomfortable part. The observable universe is not static. It's growing, but not in the way you'd expect. Every second, light from slightly more distant regions enters the observable zone. The particle horizon expands. You'd think that means we'll eventually see everything, that given enough time, the entire universe will become observable. It won't. The universe is not just expanding, it's accelerating. Distant galaxies are moving away from us faster and faster, driven by something we call dark energy. At a certain distance, galaxies are receding faster than the speed of light, not through space, which would violate relativity, but because space itself is expanding faster than light can cross it. Those galaxies are beyond what's called the cosmic event horizon. Light leaving them today will never reach us, ever, even if we wait forever. The expansion of space will always outrun the light, and as time goes on, more and more galaxies will cross that threshold and disappear from view, not because they're destroyed, but because the space between us and them is growing too fast for light to ever close the gap. Billions of years from now, an astronomer on Earth, assuming Earth still exists and anyone is still around to look up, will point a telescope at the sky and see far fewer galaxies than we see today. The universe will look emptier, not because galaxies are dying, but because they've drifted beyond the horizon. Eventually, in the far future, trillions of years from now, the only galaxies left in the observable universe will be the ones gravitationally bound to our local group. Everything else will have receded beyond reach. An observer in that distant future would look out and see a quiet, dark, nearly empty cosmos. They would have no way of knowing that billions of galaxies once filled the sky. The evidence will have vanished over the horizon, carried away by the expansion of space. So the 93 billion light-year boundary is not a permanent feature of the universe. It's a snapshot, a measurement of how far light has traveled and how much space has expanded up to this moment. In the past, the observable universe was smaller. In the future, it will be larger for a while, and then effectively smaller as galaxies drift beyond the event horizon and stop sending us light. The visible frontier is shifting constantly, and we are trapped inside it, watching the universe reveal itself one photon at a time while the rest of it slips away into the dark. That is the observable universe. A sphere 93 billion light-years across, centered on you, bounded by the speed of light and the age of the cosmos, defined not by where the universe ends, but by how far we can see. It is not the whole universe, it is just the part we have access to. And every number, every distance, every galaxy we've ever catalogued sits somewhere inside that bubble. Outside it, the universe continues, unobserved, unmeasured, unknowable. And the thing that drew that boundary, the thing that made the visible frontier what it is not a wall or a limit in space. It's a process, a relentless, accelerating expansion that has been stretching the universe since the first moment it existed. That expansion is the invisible engine, and it's been running for 13.8 billion years without stopping. Space is stretching. Right now, at this exact moment, the distance between galaxies is increasing, not because galaxies are flying through space like bullets, but because space itself, the fabric of the universe, is expanding. The ground is growing, the stage is getting bigger, and everything standing on it is being pulled apart by a force that nobody predicted, nobody expected, and nobody fully understands. This is the invisible engine, the mechanism that turned a hot, dense point 8 billion years ago into a universe 93 billion light-years wide. It has been running since the first fraction of a second after the Big Bang, and it shows no sign of stopping. In fact, it is speeding up. And the implications of that acceleration are so strange, so unsettling, that even scientists who have spent their entire careers studying it will admit they do not have a clean answer for what is actually happening. The story starts in 1929 with a man named Edwin Hubble. Not the telescope, the astronomer the telescope was named after. Hubble was working at the Mount Wilson Observatory in California, using what was at the time the most powerful telescope in the world. He was measuring the distances to galaxies and comparing those distances to how fast the galaxies were moving. The motion part was relatively easy to measure. When an object in space is moving away from you, the light it emits gets stretched. The wavelengths shift toward the red end of the spectrum. Astronomers call this redshift. The faster something is moving away, the more its light is redshifted. By analyzing the light from distant galaxies, Hubble could calculate how fast they were receding. The distance part was harder. To figure out how far away a galaxy is, you need a standard candle, something with a known brightness that you can spot inside the galaxy. Hubble used Cepheid variable stars, which pulse at a rate that correlates directly with their true luminosity. Measure the pulse, calculate the brightness, compare it to how dim the star looks from Earth, and you have a distance. It is not perfect, but it works. Hubble measured distances to 24 galaxies, plotted them against their recession speeds, and found something no one expected. The farther away a galaxy was, the faster it was moving away from us. Not a loose trend, a clean linear relationship. Double the distance and the speed doubles. Triple the distance and the speed triples. The universe was not static, it was expanding. And the expansion was uniform in every direction. This was not supposed to happen. Albert Einstein had published his general theory of relativity in 1915, and the equations predicted that the universe should either be collapsing under its own gravity or expanding. Einstein did not like that. He believed the universe was eternal and unchanging, so he added a term to his equations called the cosmological constant, a kind of repulsive force that would hold the universe in balance. When Hubble published his results, Einstein reportedly called the cosmological constant the biggest blunder of his life. The universe was expanding. The math had predicted it. The observations confirmed it. And Einstein had ignored his own equations because he did not like what they implied. Hubble's discovery became known as Hubble's law. It states that the velocity at which a galaxy is receding from us is proportional to its distance. The constant of proportionality is called the Hubble constant, and it tells you how fast the universe is expanding. Measure the constant, and you can calculate the age of the universe, the size of the observable universe, and the rate at which galaxies are drifting apart. For decades, astronomers argued over what the true value of the Hubble constant was. Early estimates were wildly wrong. Some made the universe appear younger than the Earth. Others made it twice as old as it actually is. By the 1990s, the number had settled into a range most scientists could agree on, somewhere around 70 kilometers per second per megaparsec. A megaparsec, for reference, is about 26 million light-years. So for every 26 million light-years you look outward, galaxies are moving away from you about 70 kilometers per second faster. That number has consequences. If galaxies are moving apart at a steady rate, you can run the clock backward and figure out when they were all in the same place. Do the math, and you get an age for the universe of roughly 13.8 billion years. The expansion also means that space itself is growing. Galaxies are not flying through space. Space is carrying them. Picture a balloon with dots drawn on its surface. Inflate the balloon and the dots move apart. None of the dots are moving across the surface of the balloon. The surface itself is expanding, and the dots are being pulled along with it. The universe works the same way, except in 3 dimensions instead of 2. Space expands, galaxies follow. The farther apart 2 galaxies are, the more space there is between them, and the faster that space is expanding. Here is where it gets uncomfortable. At large enough distances, galaxies are receding from us faster than the speed of light. That sounds like a violation of relativity. It is not. Nothing is moving faster than light through space, but space itself can expand as fast as it wants. There is no speed limit on the stretching of space. A galaxy 14 billion light-years away is not traveling through space at faster than light speed. The space between us and that galaxy is expanding so quickly that the distance grows faster than light can cross it. The galaxy is standing still in its local patch of space. We are standing still in ours, but the ground between us is growing at a rate that makes the effective recession speed faster than light. This is not a theory, it is an observation. We can see galaxies whose light has been so severely redshifted that they must be receding at superluminal speeds. The light we are receiving from them was emitted billions of years ago when they were much closer and the recession speed was slower. The light has been chasing us ever since, fighting against the expansion of space, and only now, after billions of years, has it finally reached us. By the time the light arrives, the galaxy that sent it is vastly farther away than it was when the photons left, and it is still moving away, faster than light, completely unreachable. So the universe is expanding, space is stretching, galaxies are drifting apart. For most of the 20th century, scientists assumed the expansion was slowing down. Gravity, after all, pulls things together. The matter in the universe should be acting as a brake on the expansion, gradually reducing the rate over time. Eventually, the thinking went, the expansion might slow enough that gravity takes over and the universe begins to collapse back in on itself, ending in a big crunch. Or maybe the expansion would slow asymptotically, approaching but never quite reaching zero. Either way, the universe was expected to decelerate. That assumption held until 1998, when two independent teams of astronomers made a discovery that flipped the entire field on its head. Both teams were studying Type 1a supernovae, exploding stars that serve as extremely reliable distance markers. A Type 1a supernova occurs when a white dwarf star pulls material from a companion star until it reaches a critical mass and detonates. Because the mass at detonation is always the same, the explosion is always the same brightness. Spot one in a distant galaxy, measure how dim it looks from Earth, and you can calculate how far away it is. Compare that distance to the galaxy's redshift, and you get a measurement of how fast the universe was expanding at that earlier time. The teams expected to find that distant supernovae were slightly brighter than predicted, indicating that the universe was decelerating. Instead, they found the opposite. The supernovae were dimmer than expected. That meant they were farther away than they should be if the universe were slowing down. The only explanation was that the universe was not decelerating. It was accelerating. This was not a small adjustment. It was a complete reversal of the expected behavior. Something was pushing galaxies apart, overcoming the attractive pull of gravity and driving the expansion faster and faster. The discovery won the leaders of both teams, Saul Perlmutter, Brian Schmidt, and Adam Rees, the Nobel Prize in Physics in 2011. And it left cosmologists scrambling to explain what was causing the acceleration. They gave the unknown force a name, dark energy. The name is a placeholder. Dark does not mean it is made of anything shadowy or sinister. It just means we have no idea what it is. Energy refers to the fact that whatever it is, it behaves like a form of energy spread throughout space. The more space there is, the more dark energy there is. As the universe expands, the amount of dark energy increases, which drives the expansion even faster. It is a runaway process. Expansion creates more space. More space creates more dark energy. More dark energy drives faster expansion. Dark energy is not a substance. It is not particles you can detect or waves you can measure. It is a property of space itself. Every cubic meter of empty space contains a tiny amount of dark energy. That amount is so small that it has virtually no effect on anything happening at human scales or even galactic scales. But across the vast distances between galaxy clusters, where space itself is the dominant thing, dark energy adds up, and it pushes. The current leading explanation for what dark energy might be is Einstein's old cosmological constant, the same term he added to his equations in 1915 and later called his biggest blunder. It turns out he was not wrong to include it. He was just wrong about why it was there. The cosmological constant represents a baseline energy density of empty space, a kind of vacuum energy that does not dilute as the universe expands. It is always there, always the same strength per unit volume, and it always pushes outward. If the cosmological constant is the correct explanation, then dark energy is built into the fabric of space itself. It is not a force that was added later. It has been there since the beginning. In the early universe, when everything was much closer together, the density of matter and radiation was so high that their gravitational pull dominated. The expansion was decelerating. But as the universe grew and the density of matter dropped, dark energy started to win. Somewhere around 5 billion years ago, the expansion shifted from decelerating to accelerating. Today, dark energy makes up about 68% of the total energy content of the universe. Dark matter, the invisible gravitational scaffolding that holds galaxies together, makes up another 27%. Normal matter, the stuff of stars and planets and people, makes up less than 5%. We live in a universe dominated by things we cannot see and do not understand. The acceleration has implications that stretch far into the future. Right now, we can observe galaxies that are roughly 46 billion light-years away. Light from those galaxies is still reaching us, stretched by billions of years of expansion, but arriving nonetheless. As time goes on, more distant regions of space will come into view. Light that has been traveling for 8 billion years will have traveled for 14 billion years, then 15 billion, then 20 billion. The particle horizon will expand. The observable universe will grow. But here is the catch. The acceleration means that galaxies beyond a certain distance are receding so fast that their light will never reach us, ever, even if we wait forever. The expansion of space between us and them is growing faster than the light can travel. Those galaxies are beyond what astronomers call the cosmic event horizon. And as the universe continues to accelerate, more and more galaxies will cross that threshold and disappear from view. Not all at once, not tomorrow, but over billions of years, the observable universe will become emptier. Galaxies that are currently visible will drift beyond the event horizon. Their light will redshift further and further until the photons are stretched to wavelengths so long that no detector will ever pick them up. Eventually, the only galaxies left in the observable universe will be the ones gravitationally bound to our local group: the Milky Way, Andromeda, Triangulum, and a few dozen smaller galaxies. Everything else will be gone, carried away by the expansion of space into a region we can never observe. An astronomer trillions of years in the future, assuming anyone is still around to look, would point a telescope at the sky and see almost nothing, a handful of nearby galaxies. No distant clusters, no cosmic web, no evidence that the universe was ever filled with hundreds of billions of galaxies. The information will have been erased by expansion. That future astronomer would have no way of knowing that the universe is 93 billion light-years wide. They would not be able to measure the Hubble constant by observing distant galaxies because there would be no distant galaxies to observe. They would not see the cosmic microwave background stretched into invisibility by trillions of years of expansion. The universe they observe would look small, quiet, and static. They would be wrong, but they would have no data to tell them otherwise. The evidence would be gone. In a very real sense, we are living in a special time, a window of cosmic history where the universe is old enough to have formed complex structures, but young enough that we can still see the distant past. We can measure the expansion. We can detect the cosmic microwave background. We can observe galaxies as they existed billions of years ago. Future civilizations will not have that luxury. The universe will have expanded so much that the evidence of its own history will be out of reach. Let's talk about the speed, because 670 million miles per hour is a number that gets thrown around when people try to describe how fast space is expanding. That number is real, but it needs context. It does not mean space is moving at 670 million miles per hour everywhere. It means that at a specific distance, the recession speed due to expansion reaches that value. The farther out you look, the faster the recession speed becomes. At twice that distance, the speed is twice as high. At 10 times the distance, 10 times the speed. There is no upper limit. Space can expand as fast as it wants, because space is not a thing that moves. It is the thing that defines what movement is. The 670 million miles per hour figure is just a benchmark, a way of converting the Hubble constant into units that feel more tangible. But the reality is stranger and less intuitive than any single speed can capture. Here is another way to think about it. Imagine two galaxies sitting 10 million light-years apart. The space between them is expanding. After a certain amount of time, they are now 10 million and 1 light-years apart. Neither galaxy moved. Space grew. Now imagine two galaxies 100 million light-years apart. The same amount of time passes, but now the distance between them has grown by 10 light-years instead of 1. 10 times the distance, 10 times the expansion. The expansion rate is constant per unit distance, but the total amount of new space created depends on how much space there was to begin with. The farther apart two objects are, the more space there is between them, and the more new space gets created. That is why distant galaxies recede faster. It is not because they are being pushed harder. It is because there is more space between us and them, and all of that space is expanding at the same rate. The acceleration adds another layer. Not only is space expanding, but the rate of expansion is increasing over time. 1 billion years ago, the Hubble constant was slightly smaller than it is today. 1 billion years from now, it will be slightly larger. Dark energy is pulling the accelerator pedal down, and the universe is responding by expanding faster and faster. This is not a linear process. It is exponential. The more the universe expands, the more dark energy there is. The more dark energy there is, the faster the universe expands. And there is no known mechanism that will stop it. The universe is not headed for a big crunch. It is headed for something much stranger. Some cosmologists call it the Big Rip. Others call it heat death. Either way, the long-term forecast is cold, dark, and empty. But that is trillions of years away. For now, the expansion is slow enough that structures held together by gravity, stars, galaxies, galaxy clusters, are not being torn apart. The Milky Way is not expanding. The solar system is not expanding. You are not expanding. Gravity is strong enough at those scales to hold things together. It is only at the largest scales, across the voids between galaxy superclusters, that the expansion dominates, and that is where the invisible engine does its work. quietly, relentlessly, stretching the universe larger every second, adding new space to the gaps, pushing the horizons farther away, creating a cosmos that is simultaneously growing and becoming less observable. So Hubble's law was not just a discovery about motion, it was a discovery about the nature of space itself. Space is not a fixed stage where events happen. It is a dynamic participant. It expands. It carries matter with it. It grows faster in some regions than others, depending on how much space there is to begin with. And somewhere in the fabric of that space, woven into every cubic centimeter of the vacuum, is an energy we cannot see, cannot measure directly, and cannot explain. An energy that has been driving the universe apart for billions of years and shows no sign of slowing down. That is the invisible engine, and it has been running since the moment the universe began, shaping everything that came after. And the light from those earliest moments, stretched and distorted by nearly 14 billion years of that expansion, is exactly what the James Webb Space Telescope was built to find. We built a telescope to look backward through time. That is not a metaphor. It is a literal description of what the James Webb Space Telescope does. Every photon that hits its mirror is a fossil, a signal from the past, carrying information about a moment that ended billions of years ago. Point Webb at a distant galaxy, and you are not seeing that galaxy as it is today. You are seeing it as it existed when the light left, back when the universe was younger, smaller, hotter. The farther out Webb looks, the farther back in time it sees, and in the last few years it has seen farther back than any instrument in history. Webb launched on Christmas Day 2021, folded up inside an Ariane 5 rocket, riding a controlled explosion out of Earth's atmosphere and into deep space. It did not go into orbit around Earth. It traveled outward, past the Moon, to a point called the second Lagrange point, about 1.5 million kilometers from our planet. At that spot, the gravitational pull of Earth and the Sun balance in just the right way that Webb can sit there, relatively stable, without burning fuel to hold its position. It is cold out there, dark, perfect for infrared astronomy. Infrared is the key. Visible light is what human eyes detect, a narrow slice of the electromagnetic spectrum ranging from red to violet. But visible light is only a tiny fraction of what the universe is broadcasting. Most of the light in the cosmos has been stretched by expansion into longer wavelengths. Light that left a distant galaxy as ultraviolet or visible blue has been redshifted so far that by the time it reaches us, it arrives in the infrared. If you want to see the earliest galaxies, the ones that formed when the universe was still an infant, you need a telescope that can detect infrared light. Hubble could do some of that, but only at the shorter end of the infrared range. Webb was built to go deeper. Webb's primary mirror is 6.5 meters across, made of 18 hexagonal segments coated in a thin layer of gold. Gold reflects infrared light better than almost any other material. Each segment is independently adjustable, aligned with nanometer precision so that the entire mirror acts as one enormous collector. Behind the mirror sits a suite of instruments, cameras, spectrographs, coronagraphs, each one designed to pull information out of the faint infrared glow of the distant universe. And between the mirror and the sun sits a tennis court-sized sunshield made of 5 layers of metallized plastic. The sunshield keeps the hot side, the side facing the sun and Earth, at around 300 Kelvin. The cold side, where the instruments live, sits at around 40 Kelvin. Cold enough that the telescope's own heat does not overwhelm the faint signals it is trying to detect. The first images came back in July 2022, and they were everything astronomers had hoped for. Sharp, detailed, flooded with galaxies that Hubble had barely been able to see or missed entirely. One of the earliest deep-field images, a patch of sky near a galaxy cluster called SMACS 723, revealed thousands of galaxies in a region no bigger than a grain of sand held at arm's length. Most of those galaxies are billions of light-years away. Some are so distant that their light has been traveling for more than 13 billion years. We are seeing them as they existed when the universe was less than 1 billion years old. Infrared astronomy does something visible light cannot. It sees through dust. The early universe was full of it. Dust clouds thick enough to block visible light completely. Stars forming inside those clouds would be invisible to a telescope like Hubble, but infrared light passes through dust relatively easily. Webb can peer through the murk and detect the heat signature of stars igniting, galaxies assembling, black holes feeding. It is like having X-ray vision for the cosmos. The stuff that used to hide things is now transparent. One of Webb's first major discoveries was a galaxy called Jade's GSZ 13-0. The name is a mouthful. JADES stands for JWST Advanced Deep Extragalactic Survey, a coordinated program designed to push the telescope to its limits. The Z13 part refers to its redshift, a measure of how much the light has been stretched. A redshift of 13 means the light has been stretched by a factor of 14. The galaxy is so far away that we are seeing it as it existed roughly 13.4 billion years ago, only about 300 million years after the Big Bang. That is early, shockingly early. Before Webb, the farthest confirmed galaxies were seen at redshifts around 11 or 12. Webb blew past that within months. Jade's GSZ 13-0 is not alone. Webb has found dozens of galaxies at similar distances, some of them massive, some of them bright, all of them existing at a time when the universe was supposed to still be getting its act together. The Standard Model predicted that galaxies in this era would be small, dim, chaotic. The first stars were just beginning to form. Heavy elements had not yet been forged in significant amounts. The universe was still mostly hydrogen and helium. Galaxies should have taken time to grow, hundreds of millions of years to pull themselves into anything resembling order. And yet, here they are, big galaxies, organized galaxies, galaxies that look disturbingly mature for their age. Some of these galaxies are so bright that their light output rivals galaxies billions of years older. That should not be possible. Brightness comes from stars, lots of stars. Building that many stars takes time. You need gas clouds to collapse. You need the first generation of stars to live and die, seeding the surrounding space with heavier elements. You need those enriched clouds to form a second generation of stars, then a third. Each cycle takes tens of millions of years at least. Run the numbers, and there is not enough time between the Big Bang and 300 million years later to build some of the galaxies Webb is finding. And yet there they are, sitting in the data, refusing to go away. The discoveries have forced cosmologists to revisit their models. Maybe star formation in the early universe was faster than we thought. Maybe the first clouds of gas collapsed more efficiently. Maybe dark matter, the invisible scaffolding that holds galaxies together, clumped together more aggressively in the early universe than current models allow. Or maybe something stranger is happening. Some of the brightest objects Webb has found might not be galaxies full of stars at all. They might be quasars, supermassive black holes feeding on infalling gas, heating it to millions of degrees, and outshining entire galaxies in the process. If that is the case, the question shifts. How did black holes that massive form so quickly? There is not enough time for a stellar mass black hole, the kind that forms when a massive star collapses, to grow to 1 billion solar masses by eating nearby gas. The math does not work. Not in 300 million years, not even if the black hole is feeding as fast as physics allows. One possibility is called direct collapse. In this scenario, giant clouds of primordial gas in the early universe skipped the star formation phase entirely and collapsed straight into black holes weighing tens or hundreds of thousands of solar masses. Start with a seed that large and you have a head start. Grow from there and you can reach billions of solar masses in the time available. It is speculative. No one has directly observed a direct collapse black hole, but it is one of the few ideas that can explain how supermassive black holes existed so early in the universe. Webb is not solving these mysteries yet. It is making them sharper. Every new observation adds detail. Every spectrum reveals another chemical fingerprint. Every deep field image finds more galaxies that should not be there. The telescope is doing exactly what it was designed to do. It is showing us what the early universe actually looked like, not what we thought it should look like. And the two do not match. Now go farther back, past the galaxies, past the first stars, past the moment when light could travel freely through space, back to a time when the universe was so hot and so dense that atoms could not hold themselves together. That era ended roughly 380,000 years after the Big Bang, and the light from that moment is still arriving, stretched by nearly 14 billion years of expansion. We call it the cosmic microwave background. The cosmic microwave background is not starlight. It is the afterglow of the Big Bang itself. When the universe was 380,000 years old, it was filled with a hot glowing fog of hydrogen plasma. Photons could not travel more than a short distance before bouncing off a charged particle. The universe was opaque. Then it cooled. Protons and electrons combined into neutral hydrogen atoms. Suddenly, photons could move without interference. The universe became transparent. The light that was freed at that moment has been traveling ever since, stretched by expansion from visible and ultraviolet wavelengths all the way into the microwave range. Today, that light fills the entire sky. It is faint, just a few degrees above absolute zero, but it is everywhere. Every direction you point a sensitive radio telescope, you detect it, a uniform glow coming from every point in the sky. The cosmic microwave background is the oldest light in the universe. It is also the most important. The CMB was discovered by accident in 1965 by two radio astronomers, Arno Penzias and Robert Wilson, working at Bell Labs in New Jersey. They were calibrating a large horn antenna and kept picking up a persistent background noise they could not explain. They thought it might be interference from nearby New York City. It was not. They thought it might be bird droppings inside the antenna. They cleaned it out. The noise did not go away. Eventually, they realized they were detecting radiation coming from space itself. The signal was the same in every direction. It had a temperature of about 3 Kelvin. It matched the predicted signature of the Big Bang's afterglow almost perfectly. Penzias and Wilson won the Nobel Prize for the discovery. They had found the echo of creation. The CMB is not perfectly smooth. If it were, the universe today would be perfectly smooth too. No galaxies, no stars, no structure. Just a uniform soup of hydrogen spreading outward forever. The CMB has tiny fluctuations, hot spots and cold spots that differ in temperature by only a few millionths of a degree. Those fluctuations are the seeds of everything that came later. Regions that were slightly denser than average had slightly stronger gravity. They pulled in more matter. Over hundreds of millions of years, those overdense regions collapsed into the first stars, the first galaxies, the first clusters. The pattern of fluctuations in the CMB is a snapshot of the universe's initial conditions, a map of the density variations that would eventually grow into the cosmic web. NASA launched a satellite called COBE in 1989 to map the CMB in detail. It confirmed that the fluctuations were there. In 2001, a more advanced satellite called WMAP produced a much sharper map. And in 2009, the European Space Agency launched Planck, the most precise CMB observatory ever built. Planck's map of the cosmic microwave background is one of the most important images in all of science. It shows the entire sky color coded by temperature. The variations are tiny, but they are real. And embedded in those variations is information about the universe's age, its composition, its geometry, and its fate. From the CMB, cosmologists have determined that the universe is flat, not flat like a pancake. Flat in the sense that parallel lines stay parallel forever. If you drew two laser beams pointing in the same direction and let them travel across the universe, they would never converge or diverge. That flatness tells us that the total energy density of the universe is almost exactly equal to a critical value. Any higher and the universe would be closed, destined to collapse back in on itself. Any lower and it would be open, expanding forever, with space curving outward like a saddle. Ours is right on the edge, flat, infinite as far as we can tell. The CMB also tells us what the universe is made of. About 68% dark energy, 27% dark matter, less than 5% normal matter, the stuff of stars and planets and people. We are a rounding error. The fluctuations in the CMB also give us the Hubble constant, the rate at which the universe is expanding. Planck's measurement gave a value of about 67 kilometers per second per megaparsec. That number has caused arguments, and we have already covered why. But the point here is that the CMB lets us measure fundamental properties of the universe by looking at light that has been traveling for more than 13 billion years. The cosmic microwave background is the farthest back in time we can see using light. Before that moment, the universe was opaque. Photons could not travel freely. Any light emitted before 380,000 years after the Big Bang got scattered and absorbed before it could go anywhere. It is like trying to see through fog. The fog is too thick. There is no window into the universe before the CMB, at least not with light. Gravitational waves might offer a way in. Neutrinos might. But photons, the particles that make up light, hit a wall. The cosmic microwave background is that wall. It is the surface of last scattering, the edge of the visible past. So Webb sees galaxies forming 300 million years after the Big Bang. The CMB shows us the universe at 380,000 years after the Big Bang. Between those two observations lies a period astronomers call the cosmic dark ages. No stars had formed yet, no galaxies. The universe was dark, filled with cooling neutral hydrogen gas, slowly clumping together under the pull of gravity. This era lasted for tens or hundreds of millions of years, depending on where you were. Eventually, the densest clumps of gas collapsed and ignited the first stars. Astronomers call them population 3 stars. They were massive, hundreds of times the mass of the Sun, hot, blue, short-lived. They burned hydrogen into helium, helium into carbon, carbon into oxygen, building heavier elements in their cores. Then they exploded. The supernova seeded the surrounding gas with the first heavy elements in the history of the universe. From those enriched clouds, the next generation of stars formed, smaller, longer-lived, more like the stars we see today. We have never directly observed a population 3 star. They are too far away and too faint, but Webb is looking. One of its major science goals is to find the signature of those first stars, either individually or as part of the earliest galaxies. The spectrum of a population 3 star would be distinct. No heavy elements, just hydrogen and helium. If Webb finds one, it will be the oldest star ever observed, a relic from the first light of the cosmos. The Dark Ages ended when the first stars turned on. Their ultraviolet light began ionizing the surrounding hydrogen, turning it from neutral back into plasma. The process is called reionization, and it took hundreds of millions of years. By the time the universe was about 1 billion years old, reionization was mostly complete. The universe was transparent again, but for a different reason. Instead of being too hot for atoms to form, like it was before the CMB, it was now filled with ionized gas, kept that way by the light from billions of stars. Reionization marks the end of the Dark Ages and the beginning of the era we can observe with telescopes like Webb. So here is the timeline. The Big Bang happens. The universe expands and cools. At 380,000 years, it becomes transparent. The CMB is released. The universe enters the Dark Ages. No stars, just hydrogen. At some point between 100 million and 300 million years, the first stars form. Reionization begins. By 1 billion years, the universe is full of stars and galaxies. Webb is observing the tail end of this process. The galaxies it sees at redshift 13 are among the earliest to form. They are not the first stars. Those are still hiding, but they are close. And every observation Webb makes brings us closer to seeing the moment the universe woke up. There is a limit to how far back we can see, and it is not the Big Bang. The Big Bang itself is not an event you can observe. It is a singularity, a breakdown in the equations, a moment where the laws of physics as we understand them stop making sense. The observable past begins at the moment the universe became transparent. Before that, there is no light to observe. Before the CMB, we are working from models and indirect evidence, not direct observation. The earliest fraction of a second after the Big Bang is described by theories like cosmic inflation, a period when the universe expanded faster than light for a brief moment, smoothing out irregularities and setting the stage for everything that followed. Inflation explains why the universe is flat. It explains why the CMB looks so uniform. It explains the origin of the density fluctuations that became galaxies. But we have no direct evidence that inflation happened. It is a model that fits the data, not a thing we have observed. Some physicists are working on ways to test inflation. Gravitational waves from the inflationary era might still be rippling through space, too faint to detect directly, but potentially leaving an imprint on the polarization of the CMB. Experiments like BICEP and the upcoming Lightbird satellite are searching for that signal. If they find it, it will be the first direct evidence of what happened in the first trillionth of a second after the Big Bang. If they do not, cosmologists will have to rethink the entire framework. Webb is not looking at inflation. Webb is looking at galaxies, stars, black holes, the structures that formed long after the inflationary era ended. But every galaxy Webb finds, every spectrum it captures, adds a piece to the puzzle. The early universe is no longer a blank space in our models. It is becoming a detailed map. We know what galaxies looked like at 300 million years, at 500 million years, at 1 billion years. We know how star formation rates changed over time. We know when the first heavy elements appeared. We know when supermassive black holes started growing. The timeline is filling in, the story is coming together, and the story is stranger than anyone expected. Galaxies formed faster, black holes grew bigger, stars ignited earlier. The universe was not a slow, orderly process. It was chaotic, violent, efficient. The first billion years of cosmic history were a frenzy of activity, and the evidence is sitting in Webb's data archives right now. Astronomers are still sorting through it. Every new deep-field image reveals more galaxies. Every spectrum contains more surprises. Webb has only been operating for a few years. It is expected to last at least a decade, maybe longer if the fuel holds out. A decade of staring at the earliest galaxies. A decade of watching the cosmic dark ages end. A decade of pushing the boundary of the observable past closer and closer to the beginning. But there is still a gap between the CMB and the first galaxies. Between 380,000 years and 300 million years. A stretch of time where the universe existed, but we cannot see it. Not yet. Maybe not ever. At least not with light. That gap is the frontier, the edge of what we can observe directly, and beyond that edge lies the question that has been lurking since the beginning. If the observable universe is 93 billion light-years wide, and the universe beyond that is unobservable, what is out there? How much more universe is there? Is it infinite? Is it finite? Does the question even make sense? That is not a question Webb can answer. It is not a question the CMB can answer. It is a question that requires a different kind of thinking, a different kind of evidence, and that is exactly where the conversation goes next. There is a boundary to observation, not a wall you could touch, or a surface you could photograph, but a hard limit to how far light can travel in the time the universe has existed. Stand at the center of your own observable sphere, 93 billion light-years wide, and you are surrounded by everything you can ever hope to see. Stars, galaxies, the cosmic microwave background glowing faintly at the edge of time. And then nothing. Not darkness in the way you understand it, just the absence of information. No photons have arrived from beyond that boundary because there has not been enough time for them to get here. So the question stops being, what do we see? and starts being what is actually out there. This is not a question science was designed to answer. Observation is the backbone of the scientific method. You look at something, measure it, test it, build a model that explains what you saw, and then you look again to see if the model holds. But if something is permanently beyond your ability to observe, the rules change. You cannot measure it, you cannot test it directly. You are left with logic, mathematics, and assumptions, which means you are guessing, even if the guesses are educated and grounded in the best physics we have. And the two main guesses, the two possibilities that cosmologists take seriously, are so fundamentally different that accepting one over the other changes what the word universe even means. The first possibility is that the universe is infinite. Not infinite in the vague poetic sense, where people say the possibilities are infinite or the stars go on forever. Infinite in the most literal, unforgiving sense. Endless, no edge, no boundary, no center. Space stretches outward in every direction without stopping, filled with galaxies, stars, planets, all the way to eternity. If this is true, then the observable universe, the 93 billion light-year bubble we live in, is not special. It is just one region among an infinite number of identical regions. Beyond the horizon, space looks the same. Same density of galaxies, same distribution of matter, same laws of physics. The only difference is that the light from those regions has not reached us yet, and depending on how fast space is expanding, it may never reach us. But it is there, real, physical, filled with structure, an endless continuation of what we already see. The second possibility is that the universe is finite. It has a size, a total volume. You could, in principle, measure it and get a number. That number would be unimaginably large, far bigger than the observable universe, but it would still be a number. Finite does not necessarily mean there is an edge in the sense of a wall or a barrier. The universe could be shaped in such a way that it curves back on itself. Travel far enough in one direction and you end up where you started, like walking around the surface of a sphere, no edge, but still finite. A closed universe, bounded but without a boundary. If this is true, the observable universe is a piece of something larger but measurable. Space is real, but it does not go on forever. There is a total amount of it, and we are seeing a fraction. Both possibilities are consistent with everything we have observed so far. That is the uncomfortable part. The data does not prefer one over the other. Measurements of the cosmic microwave background, the most precise map we have of the early universe, suggest that space is flat. Parallel lines stay parallel. Triangles add up to 180 degrees. Flat space, in the context of general relativity, implies infinite space. If the universe were closed, curved back on itself like the surface of a sphere, we would expect to see a slight curvature in the geometry of the cosmos. We do not. The measurements say flat to within the margin of error, and flat, according to the math, means infinite. But the margin of error matters. The curvature could be so slight that we cannot detect it yet. A sphere large enough looks flat when you are standing on its surface. Earth looks flat from the ground. It took global navigation and high-altitude observation to prove it is round. The universe could be the same way. Curved, closed, finite, but so large that the curvature is invisible from our vantage point. If the total size of the universe is 1,000 times larger than the observable universe, or 1,000,000 times, or 1 billion times, we would not be able to tell the difference. The part we can see would look flat no matter what the true shape is. The measurements we have rule out a small closed universe. They do not rule out a very large closed universe. So the data leaves the door open to both answers. Cosmologists rely on something called the cosmological principle to make progress. It is an assumption, not a proven fact. The principle states that the universe is homogeneous and isotropic on large enough scales. Homogeneous means it looks the same everywhere. Isotropic means it looks the same in every direction. No special locations, no preferred directions. If you could teleport to a random spot 100 billion light-years away, the universe there would look statistically identical to the universe here. Same kinds of galaxies, same density of matter, same expansion rate. The cosmological principle is baked into every major model of the universe. Without it, the equations become unmanageable. You would need different rules for different regions, and there is no way to test that. So cosmologists assume uniformity and build from there. The principle is not pulled out of thin air. It is based on observation. Within the observable universe, on the largest scales, the cosmos does look homogeneous and isotropic. Galaxies are not distributed randomly. They cluster together in groups. Groups cluster into superclusters. Superclusters form filaments stretching across hundreds of millions of light-years. But zoom out far enough, and those filaments smooth into a uniform distribution. The cosmic microwave background, which shows us the universe at 380,000 years old, is almost perfectly smooth. The temperature variations are tiny, only a few parts per million. That smoothness suggests the universe was uniform back then, and if it was uniform then, it is probably uniform now. And if it is uniform within the observable universe, the safest bet is that it stays uniform beyond the observable universe. But safe bets are not certainties. The cosmological principle is an assumption. A useful one, a reasonable one, but still an assumption. There is no way to prove that the universe beyond the horizon looks like the universe inside the horizon, because we cannot see it. The principle works as long as the universe is infinite, or as long as the finite universe is large enough that its boundaries are far beyond our reach. But if the universe has an edge, a real physical boundary where space ends, the principle breaks down at that boundary. And if the universe is not uniform beyond the horizon, if there are regions where the density is different or the laws of physics operate under different constants, the principle breaks down there too. We would have no way of knowing unless the effects of those differences somehow rippled into the observable universe. So far, no one has found convincing evidence of such effects, which means either the universe is uniform or the non-uniform parts are far enough away that they do not matter to us. Now let's talk about edges, because the idea of space having an edge is one of the hardest concepts in cosmology to wrap your brain around. If the universe is finite and has a boundary, what is on the other side of that boundary? The instinctive answer is nothing, empty space, a void. But that is not right. Space is not a container that holds things. Space is the thing. If space ends, there is no other side. There is no void beyond it. There is literally nothing. Not blackness, not emptiness, nothing. No dimensions, no time, no potential for anything to exist. The concept does not fit into human intuition because we are used to boundaries being